Today I would like to talk to you about how we use the nLIGHT's AFX1000 laser in our university, and more specifically how we try to simulate the process windows and the improved process windows that this laser allows us to achieve. So I'll quickly talk about how we integrated the laser in our system, and then I'll mostly focus on how we simulate the melt pool in the different intensity profiles of the AFX laser, and how we use the simulated melt pools to predict process windows. So we retrofitted the AFX1000 into one of our existing systems, but we did change the software to a fully in-house developed system, which means that we have control over the vector ID, and thus the intensity profile of the AFX1000 to a vector ID level, which means that we can switch our intensity profile not within a job or within a layer or within a part, but actually within a part itself. For example, a contour with a fill with a different intensity profile, which allows us to take full advantage of the different beam profiles in the AFX systems. But we took a machine with a 100 watt laser and put a 1.2 kilowatt laser in there. So first thing we did is validate that the system still operates normally. So here you can see a parameter variation in the standard Gaussian mode, index 0, and we can still achieve 99.99% density. In itself, this is not very interesting, but I'll come back to this later in the presentation. The second thing we did is something similar, a parameter variation with different intensity profiles, varying from a tiny bit of energy in the ring mode of the beam until almost fully a ring mode melting. And you can indeed see that we achieve, at least for Archimedes density, almost dense parts. Optically speaking, we achieve 99.97% for the ones that we test. Now, I'll come to the simulation part. Finding the optimal parameter set for a standard Gaussian beam means many different experiments were varying the power, the speed, the hedge spacing in your system. But by using this variable beam profile, you add another layer of complexity on top of your optimal parameter variation, which means a lot of experimental work. So what we try to do is to simulate the process to guide us in the right direction, in a sense, reducing the amount of experiments needed to be done to find the optimal parameter set. You can do this in two ways. You can start with a high-fidelity multi-physics simulation, but then every parameter set will take you hours or days to simulate. What we did is we threw overboard half of the physics. We don't look at fluid dynamics. We only look at steady-state melting. But still, we can achieve the dimensions of the melt pool up to 10 to 15% accuracy, which is sufficient to generate the process windows what we want to do. And this model is already validated for a Gaussian beam, so we extended it to use the different intensity profiles. So here you see an intensity profile measurement of the standard AFX in its Gaussian mode. And this is important because for our simulations, the spot size is crucial. In a standard Gaussian mode, it's quite simple. You approximate it as a Gaussian beam and you have a beam radius A. But if you do this for a different profile, one beam radius is not enough to accurately describe the intensity profile. So we approximated this as the center still a standard Gaussian beam with your beam radius A. And the ring around is a one-dimensional ring with a radius capital R, and superimposed on this, a Gaussian with a radius small r. And by combining the center radius A and big R and small r, we can accurately describe the intensity profile. And you can get these kind of simulations from it. On the bottom, you see the different intensity indexes of the AFX laser in our simulations, which correspond pretty well to what we actually can measure in the system. And now that you have this, we can implement this in our melt pool dimension model, and look, we can get these kind of pictures. So you see the different melt pool index and the resulting melt pool dimensions as a top view. What we see is a reduction in melt pool length and an increase in melt pool width, and they also get a little bit less deep, so a little bit shallower. And this reduction in melt pool length is quite significant because that means that we get a more stable melt pool. Because if your melt pool gets very elongated, at a certain point you will achieve balling, where you don't longer have a very continuous track but different beats. And this I will show in the next slide as well. Now that we have these melt pool dimensions, we can try to predict the process window in our system. To do so, we have to put some boundary conditions on what is a good melt pool dimension. So we want sufficient depth so that you can fully melt a single layer of powder. We don't want keyhole melting, so we put a limit to how deep the melt pool can be corresponding to its width. And we also want the stable melt pool, so we must limit the length of the melt pool can have relative to its width. And then we can get these kind of process windows. I'll start on the left with the one for the standard Gaussian index. The red process window is for 30 micron layer thickness, green is for 60, and blue is for a 90 micron layer thickness. And this is quite normal, what you're used to see. So it's limited by minimal depth, maximal keyhole, and the stability criterion. What's interesting is now, if we do the same for the different intensity profiles, for example, here on the right, you see the full ring mode, we see a significantly increased process window. Why is this? Well, for one, as I said, the melt pool is shorter, which means we can push up this boundary limit of where it becomes unstable, which allows us to use higher production speeds, scanning speeds. And because we have a wider melt pool, we also can increase the hedge spacing. And what's actually counterintuitive is that we also have an increased process window for the deeper layers. You would say it's a shallower melt pool, sure, that's quite counterintuitive, but you have to think in it the other way around. Because we decreased the depth, we can put more power in the system before we reach the keyhole mode melting and the corresponding keyhole pores. So we can increase both the depth, the hedge spacing, and the speed, clearly showing the potential productivity increases. In our simulated process window, we see increases of more than 3 times the productivity without any defocusing, without any special system, just switching the laser intensity profile. Now this side I showed you before, the standard Gaussian mode and a varying amount of parameters. We can now plot these parts, which are all dense, on our simulated process window to see how well it corresponds to reality, because these simulations are very nice, but if they don't correspond to reality, they're useless. And indeed, we see that my tested parameter set nicely falls within the process window, which is an indication that we are looking in the right direction. Now it becomes more interesting if we go back to this slide, where I varied the different intensity profiles. And if we plot this on the index, on the simulated process windows, we see for the index 1 that my parts that in reality led to dense parts falls nicely within the process window up top. But the one at the bottom, where we use the ring mode, the parameters here at the very edge do correspond nicely to the parameters that are no longer yield dense parts. So this is again an indication that we are looking in the right direction with our process window simulations. Now, of course, to fully validate the model, we want melt pool dimensions and not just density of cubes. So the next work we're doing is building substrates and scanning single lasers with varying power, speed, intensity profiles, and then measuring the melt pool dimensions to see how well my dimensions from the simulations correspond to the actual dimensions within a part. Which brings me nicely to our prospects and conclusions. I showed you how we can simulate quite easy the process, even though we only look at thermal simulations, and how we predict productivity increases of up to 3 times without any special defocusing. And actually, I will give you a sneak peek at how this can be implemented in reality. Up top, you see an impeller design that's processed in the standard way, Gaussian mode. On the bottom, you can see the same design, but now in a multi-index processing, where the contour is scanned with your standard Gaussian, the same parameters as the one at top, and you see similar surface quality, but the filling is done with the donut laser. And what we see is a doubling of the theoretical productivity. And this is not even the most optimal parameter set for productivity. This was just a set that we know yields dense parts. And I can already see a doubling of productivity. And if you look at the amount of energy we put into a single volume of metal, we actually increased or decreased the energy required to melt material by 20%. So without even trying, we doubled the productivity and reduced or increased the energy efficiency. So now our next steps, first of all, as I said before, we want to validate our model to truly show that it predicts the melt pool dimensions. And then we want to increase this productivity rate, for which I gave you a sneak peek, our true industrial parts, not just the cubes that everyone is using. And then finally, We also want to check that the mechanical integrity of these multi-index parts still can achieve the same values as the one we have in standard processing. Which brings me to my last slide. I must acknowledge the FWO for funding this research, and of course the help of all of my colleagues who are present here. If you have any questions, I'll be happy to answer them now, or you can also find us in our booth upstairs as part of the From 3D booth. Thank you.